So next up, we've got Mike Fowler, who's a principal data engineer at Clarinet. Mike, I had an email forwarded to me from Mike earlier in the week, and his list of certification badges is actually longer than the content of the text of the mail. So obviously, Mike's been tracing his certifications like Pokemon. He has, in fact, been catching them all, including all of the specialties and the professional cert. So good work, Mike. I know it's a lot of time and effort taken to get through that. Mike believes, driven by belief that humans should only do interesting things, and uses his years of experience to build reliable, scalable, and repeatable data pipelines and platforms. Particularly enjoys taking customers on the journey from descriptive analytics to prescriptive analytics, which is terminology that I'm not familiar with, actually. Mike's an open source advocate, having contributed to Postgres, Terraform, and YAWL, which, again, I'm not familiar with. Look, I just do emails and spreadsheets these days. I don't know what half of this stuff is. Mike speaks regularly at conferences and meetups, sharing interesting ways to make great use of data technologies. And when not parked behind a keyboard, he can be found amongst his 5 children, delighting them with his finest dad jokes, some of which I'm hoping will make it into your slides, Mike. Over to you. Let's unmute you, shall we?
Hello, yeah, sorry. As soon as I clicked on share screen, I lost the ability to unmute myself. So let me bring that back up again.
Cool. I can hear you now, loud and clear.
Good, okay. So just restart that presentation. And then we'll share that again. And I might just lose the ability to mute or unmute, but that'll be fine.
It's fine.
There we go. Okay, share that screen.
Great. Yep,
okay.
I can see that.
Great. Okay. Thank you. So, yep, I'm Mike Fowler, Principal Data Engineer at Clarinet. So I thought I would start with a little bit about myself. Wow, okay, now I've lost the mouse. Well, technical problems, but there we go. So I started off as a programmer. Java still in my background, but, you know, please forgive me. I have been using Python and Go more recently. But one thing that always came in with any programming I was doing was data. And in fact, I fell in love with the Postgres database a very long time ago. So I've contributed, in fact, to Postgres, YAWL and Terraform, as was mentioned there. And I'm a certified data management professional through DAMA. And yep.
Just to stop you there, Mike, you've got a something over the top left of your window is actually occluding your slides. Yeah, that's perfect.
There we go. Great. Okay. So yeah, I've collected a bunch of AWS certifications along the way, including all of the data certifications. And hopefully that's responding now. There we go. Okay, so but of late, I have been very focused a lot on these kind of data tools. So things like scikit-learn, Kafka, Apache Beam, Jupyter Notebooks, TensorFlow, and just to sort of give them their due, I do have some certifications on some other clouds. So the main thing that I want to sort of you to take away from there is that I like to think that I know data. So you may have come across this article that's been sort of said by a lot of people over the years that data is the new oil. And perhaps to update that for these strange times that we live in, perhaps toilet paper is the new oil and data is the new toilet paper. So the reason for this is that a lot of businesses get a lot of their modern value from data itself. But let's go and sort of look at where that started from. Now, if we think going back, say, 10, 20 years, data warehouses is where we derived all of the intelligence about our business. We looked into what was happening in our business yesterday, perhaps the last few months, compared it to previous years, and we've spent a lot of time shaping our data to get it into that data warehouse. And if we look at how we get that data there, Typically, we have a bunch of different data sources. These can be relational databases like Postgres, SQL Server, files like CSV files, or other sort of services pushing to. Now, typically, the way we get data is we pull it from these systems. So there's a nightly batch job that runs and pulls out all the data that we need for loading up our warehouse. Now, these are usually transformed in some way to fit the model of the data warehouse. This is typically a bunch of scripts that are run, and eventually all our data is there. And this is the extract, transform, and load process, or ETL, that most people are pretty familiar with. Once we've got our data into that data warehouse, we can have our wonderful dashboards, and brilliant, we're happy. We can look into our business. But there are some challenges to this particular approach, which has worked very well for a long time. One is that we can pull far too hard on our source systems. Interested that Phil mentioned there that using DMS was hurting SQL Server too much, and I've come across that same sort of problem. If we hit the source systems at the wrong time of the day and try and pull out a mountain of data, we can end up in a situation where we've taken out production simply because we want to get analysis data. Another problem is lag, or the timeliness of the data that we actually have there. Because of the fact that we do tend to run these load jobs overnight, we are looking the next day at data that's at least 12, 24 hours behind what's happening in our business right now. And this can lead to a interesting delay in making decisions. You look at something that happened yesterday, reacted to it, but perhaps that problem's already sorted itself out. You can flood your warehouse. If you've suddenly had a big uptick in sales and you've got a lot of data that's come in and you push that into your warehouse, if you haven't sized that warehouse appropriately, you can just topple it over. Flooding can take on other shapes as well, in that if you're getting too much data coming in, you might start hitting funny indexing problems where your dashboards now take too long to load. And actually, I think the biggest problem here is that we've actually kind of put the model before our loading. So we spend a lot of time up front building a model to match what we believe our business looks like, and then we shape the data and stuff it in. And the problem with this is that we might not have realized that there's some key activity happening in our business. A company that I did some work for that sells pizzas, they were utterly obsessed with the idea that delivery time for their pizza was actually what drove customer feedback. But actually, they learned when they started looking at the data, it had nothing to do with how fast the pizza got to them. It was all to do with the temperature that the pizza was when it arrived. Now, if you haven't even started recording the fact that your pizza has a temperature or an arrival temperature, then you're not going to have that in your warehouse, and this could be a whole thing you're not even considering. And of course, changing the model once you've built it is really expensive. Could be monetary, but more often than not, it's time, because you have to go and reload all of your historic data to get perhaps some attributes that you overlooked, like this temperature of a pizza, just so that you can now get it into your warehouse. And so you end up coming across analysts to say, the model's not right, but I'm not going to fight the team to change what it looks like. So here we are, the data lake. It's going to solve all our problems. It looks wonderful. It's nice and pristine. We're going to dump all this data into one location instead of a warehouse. We're not going to model anything, and wonderful. So same idea. We got a bunch of data sources. Typically, we extract data from them. We throw it straight into the data lake, and then later on, we do some transformation on that to do our dashboards. But we've solved one of the problems. Our storage is now independent of our compute. So we can just keep throwing data in there on a nice scaling storage platform like S3, and we can then work with the results later on. And we're not going to flood the database simply because the rate of data ingestion has suddenly changed. We can now model on demand. because we haven't actually enforced a model when we loaded the data, we can just start playing with the data, come up with a model, see what fits, and experiment. But we're still pulling too hard on the source. And we haven't actually solved the lag in the timeliness issue because we're still pulling data in overnight. And one of the big problems introduced is the sort of data swamp. We've just got this unmaintainable mess of data collecting in some S3 bucket. Maybe we've partitioned it, maybe we've got it in some sensible storage format like Parquet or Avro, but more often than not, it is just a horrendous dumping ground of data that's rotting away. So, data streams. This is a way that are kind of a halfway ground between both of these sort of data lake and data warehouse type approaches. We start off with some data sources. We push the data into a stream. We store it in a data lake, and then we start processing it. But yeah, you're just sort of now looking at me going, well, Mike, you've just kind of done the same thing, but the only thing you've changed here is that you're pushing the data instead of pulling it. How is this really any different? Well, if we go back to that analogy of the data being the new oil, I don't really think it is oil. I think if we think of data as more water, it's actually a much better approach. Because if you think of something like the water cycle, water is valuable in whatever state that it's in. And it doesn't lose its value just because it's transitioned from a solid into a gas, ultimately becoming a liquid again. It's something that we can continue to get value out of as long as we can get the data. So if we start thinking about data as being something we continually work with instead of something that we look at once and then forget about, it actually starts to change the way we think about this particular handling of our data. And so if we look here, you'll see this kind of feedback starts to come in. If we start processing the data, we put it back into a stream, we store that, we process it again, we can continue to refine our data and continue to drive insight out of it. So let's kind of look at a pattern of how you put together something like this before we look at a problem solved using this kind of approach to data analytics. So the stream, of course, is the central piece to this. There's a lot of different technologies that can be used for that. Things like Kinesis, Kafka, PubSub, if you're out in Google, lots of different ways to have something that you publish data to, that people can subscribe to and do what they want with it. So we're pushing data into one end of our stream, and in its simplest form, we then consume it maybe in some sort of real-time dashboard. So as data comes in, we can present it and see, we got 39,000 page views, and actually we know that that's down 14% from what we had perhaps yesterday or perhaps an hour ago. But the useful thing about a stream is that it isn't just one sort of pipeline. You can have multiple consumers that all see that data. So we can populate a data lake from our stream at the same time as we're doing our real-time analytics. From our data lake, we can start doing that refining of the data, we can do that modeling, we can start doing the data science, perhaps build out machine learned models. And if we do that, we can, through that data stream, we can perhaps make inferences as we're receiving the data. So not only do I know what my page views are, I can perhaps ask a model, do I think, given on what's happening right now, the page views are going to go up, or are they going to go down? Of course, we can also populate the data warehouse from what we're sending to a data lake. In fact, depending on how we're doing it, we could populate both at the same time. So if you use something like Kinesis Firehose, you can send everything to S3, and an S3 copy job runs to load into Redshift. We can keep that data in S3 and our sort of lifelong data lake, but we've got it in our data warehouse. And those historic dashboards can still be built on top of that data warehouse. So we're not invalidating the years of work that have gone into the traditional data warehouse models. So mention that there's a lot of different technologies that we can use, and here's just a sort of flavoring of some of them in AWS. We can start a pipeline using the simple queue service. Now, we'd actually end up chaining a lot of things together, but it is a simple starting point. We don't have to run a huge expensive Kafka cluster if all we're doing is taking simple reactions to have my ad been clicked on, for example. There are streaming pieces that we can use, like Kinesis data streams, so we can link together a bunch of things and do sort of move our data from one place to another. And we can use glue jobs as well to integrate into other places like the relational databases. Phil mentioned the database migration service. That's something else that can be used to get data into one of these streams. We've got lots of options for storing the data. We can put it in Redshift, which is the more sort of traditional data warehouse, although it does behave quite differently than the big, huge monolithic data warehouses of yesterday. We can throw stuff in DynamoDB, nice semi-structured document storage, or completely unstructured in S3, as I've been using as a sort of my example. We can do batch processing on top of that with services like Elastic MapReduce, or we can do streaming analytics with Kinesis Data Analytics. And ultimately, we can do all of the SageMaker modeling that Phil was talking about earlier. So let's put some of this together and get an idea of an actual use case for this sort of approach to data analytics. So some of you may have experienced being on call. If you haven't and you're a parent and you've got a young child, the experience of being on call is actually quite similar in that usually at the most inconvenient times, you've stayed up late working on a problem, you think, right, I'm going to get 4 hours sleep, you go to bed, and it goes off, either being the pager or the baby. And in fact, at 3 in the morning, rebooting a baby isn't really that much different than changing a nappy on a server. So our scenario, our engineer here is sound asleep, and pager goes off, you know, they're wide awake, they jump out of bed, fire up the laptop, and then the incident resolves right away. They haven't changed anything, and they haven't even managed to log in yet. Maybe the laptop's not powered on, but it's resolved. Probably the most frustrating thing you can experience as an on-call engineer, because of course you're wide awake now, the adrenaline's pumping, and it's going to be a good, you know, half an hour before you're able to go to sleep. And so here's our problem. Many PagerDuty incidents resolve before I respond, disrupting my sleep needlessly. Here's an example from PagerDuty being integrated into Slack. And we can see at 12:12, which perhaps isn't so bad for some people, it triggered. 12:13, my colleague Stephen acknowledged it. And at, I think it's 12:13 as well, it was resolved. So Steve, if he was asleep, he's been woken up, it's fixed itself, he hasn't done anything, that's a pain. So I built a bot, Mr. Data. He can take the incoming incident coming from PagerDuty, and he can make an inference. So here we are. He has, with typical precision for an Android, 77.01755% probability that the incident is going to resolve inside of 3 minutes. And in fact, it only took 50 seconds for it to resolve. So walk you through now how that's put together. PagerDuty is capable of calling an endpoint. So we can send data into a Lambda function and put it straight into our data stream. Now, in order to build a model that's able to infer whether a new incident is going to be resolved really, really quickly, we need to capture that data. So we need to build out a data lake, just keep track of every incident. Thankfully, PagerDuty does have an interface that allows you to go and download all of the historic incidents, so you can actually backfill your data lake with a big pile of CSVs to get yourself started. So Unsurprisingly, we're doing our data refining on top of that. I used scikit-learn, as it happens, to train a model inside of SageMaker. And now when that incident happens from PagerDuty, we've got a Lambda function that's called, putting it into Kinesis. That's actually quite important because you could, in the initial Lambda function responding to PagerDuty, go and make your inference at the sort of same time, but PagerDuty expects you to be fairly responsive. And so what happens is that while you're busy waiting to get an inference from your model, PagerDuty thinks you haven't replied, so it sends you another webhook call. And before you know it, you've got a big queue of things making multiple inferences. So we've got a Lambda function that says right back to PagerDuty, yep, got that, put it into Kinesis, and off the back of that, Kinesis being our data stream, we're able to chain everything else. So we've got our fire hose sending stuff off to the lake, and we've got another Lambda function making the inference, and ultimately publishing it into Slack. So one important thing to note is that you want to also keep track of those predictions. So it's not just that you have, you know, collection of data and you kind of continue to refine. It's useful to know whether your model is making good predictions or not. And from that, you can work out whether it's time to retrain a model or perhaps something's fundamentally changed in what's happening in your systems. Of course, we can send this data into our Redshift data warehouse, and we can present dashboards to see who's being disturbed the most, which customer is the noisiest, which services are disrupting us, you know, the most. So just to kind of layer all those AWS services on top, we've got the Redshift as our data warehouse. We've got S3 acting as our data lake, SageMaker doing both our modeling and model hosting for the inferences. We've got Lambda functions, Kinesis Firehose to sort of be the data stream, be the pipeline. And as I said, we can use sort of data streams, rather, was doing the hosting, but Firehose is sending the data off to the data lake and actually straight to Redshift. So this is where we are kind of buy one, get two free on the AWS services. So just to kind of strip that back, we can see these are the handful of AWS services that satisfy this pattern of taking data, taking a copy of it, making real-time inferences as the data is arriving. And if we go and look at the problems that we had with the sort of pure data warehouse approach or the pure data lake approach, we had pulling still too hard on the systems. We still had lag on the kind of business intelligence that we're doing, and we'd built a data swamp. So we solved the pulling too hard on the systems by pushing data, and that's different things like the database migration service doing change data capture, or having services like PagerDuty posting to an API for us. But you can also do things like have a trigger fire from inside your database that updates perhaps when an order completes, it sends the complete order. So instead of doing full change data capture, you can just send from your database or elsewhere, and perhaps you have a nicely microservice orchestrated platform, and there's a decent place where you can just send an event off to something like Kinesis. We've also solved the timeliness problem because we're able to make decisions on the data that's coming into our business right now. So that PagerDuty piece, we can have the bot effectively be on call, and if it's confident that a incident is going to resolve inside of 3 minutes, we don't need to disturb a on-call engineer. If it's something it's really not comfortable saying, there's only 10% chance that it's going to resolve, perhaps we escalate that right away, or perhaps there are scenarios where we know that, you know, this is something that has to be fixed by a person. Maybe a customer has called an out-of-hours phone line and needs to speak to somebody. But the crucial point here is that we're doing this in a very timely manner. So inside of 3 minutes of an incident occurring, we're making decisions on what to do with this incident. And of course, the stagnant data swamp, if we're continually refining our data, continuing looking after it, looking for new insights, continually modeling, we're not just building up a big, huge expense in S3 charges. We can make sure that the data is useful. And if we think that this particular data is no longer usable for us, we can archive it away or ultimately delete it. So there we are. Say goodnight from our bot and open up for questions.
Cool. Thanks, Mike. We do, in fact, have some questions in the Q&A box. So first up, Sergey asks, what are your thoughts on the data mesh approach promoted by ThoughtWorks as the next generation of data platform architecture coming after data lakes? Briefly, the idea is that even though in software architecture we're moving from monoliths to microservices, in data platforms, monolithic architectures dominates. What if our data platform will be more microservice styled?
Yes, I have come across that, and I think there is some interesting things to explore there. A similarly related concept is data virtualization, where instead of trying to get all of the data that you're interested into a single place, you actually integrate multiple data services in a single sort of data plane. I think data streams is very close to being part of that data mesh, where we've got lots of different places where we can connect bits and pieces. The challenge, of course, same challenge we've seen in microservices, is how best do we orchestrate this so that we know that all of the data decision points we're interested in are being triggered in an appropriate order. So I think it's certainly an area that's going to develop.
Cool. A question from Manju, who asks, as you mentioned the talk about the DMS lag, in fact, we're seeing this when we're pushing data from source database of Aurora Postgres to downstream teams using Redshift. How do we mitigate this kind of scenario? You may have covered this actually in the content, but maybe a recap.
So you can look at sort of carving up how you're sending the data. So the challenge with DMS is that ultimately you're serializing the whole database through a single sort of pipeline. That's only going to be so fast. So you can actually configure DMS to only be interested in a handful of tables, and you could run multiple DMS services looking at different sets of tables. An alternative is to hook on a different change data capture system. There is the Debezium Kafka Connect plugin. That is something that you can use to pull data out as it's occurring. And also, again, in the Kafka land, you can just use a JDBC connector, again, to selectively pull tables rather than pull everything that's happening in the database.
Cool. Thanks, Mike. One final question then from Jamie French, who says, hi, Mike, great visuals and delivery. Always nice to start with some praise. How would you apply observability within the solution with the array of services adopted?
Okay, so the key thing is to understand what each of the services are doing in that process and what impact those particular pieces, if they're not behaving well, would have in your sort of end-to-end solutions. So any of the managed offerings from Amazon, we can look at CloudWatch metrics. We can set up CloudWatch alerts on those. But the Lambda functions, that's kind of down to you. You can write a silent but deadly Lambda function that does what it's supposed to do, outputs absolutely nothing, and you kind of got to trust that that's doing the right thing. So to save your future self effort, make sure that you're saying, this is what I'm doing, I'm here, so that when strange things happen, maybe something's odd about the data that's causing some exception in Python to throw straight out, and you end up with a bad handler inside of the Lambda wrapper, and that gets swallowed. You don't end up spending hours and hours chasing your tail. This Lambda function took this piece of data, it tried to do that, and it didn't do this because of whatever. So it's you kind of very much build it in from the start, understand what your components are doing, and then make sure that they tell you what you're doing so that you can then, through tools like CloudWatch, see retrospectively what's going on.
Cool. So usual story, like, please, for the love of God, make your software tell us what it's up to. The usual developer operations conversation.
Yep.
Great. Thanks very much, Mike. Great to hear that. This evening's talks have been really interesting for me. I've not really worked heavily with the sort of big data and ML stuff, so some great knowledge for me there as well.